Well, now we are going to talk about password-based key derivation function version 2, and just before jumping into that right away, we are in need to know that why PBKDF2 is used at all. Before that, we need to know something about encryption. So we already know that the process of converting plain text to ciphertext and from ciphertext to plain text using a key is called encryption, right? But what we don't know till now is that the key should be of a specific length depending upon the encryption algorithm. For example, in this video, we are going to be using AES because a modified version of AES is used in WPA2, which is the CCMP. So AES takes in the key length of 128, 192 and 256 bits. You can use any of them. The more the merrier. So it's very impractical for every users in the world to give a password which is exactly of size 128, 192 and 256 bits. Also, it's very insecure for the password being directly used for encryption as the key. So because that is very much susceptible to brute force attacks. Remember anything about calculation to map data of an arbitrary size to a fixed length? Yes, I'm talking about hashing. So for example, SHA-256 provides a fixed length hash size of 256 bits. So what we can do is we can take a password, then hash it with SHA-256 and then use the resulting hash as the key that is going to be used for the encryption. Now, is that very much secure? Well, no, because in this case we are not using hashing just to verify authenticity of a data. We are using the resulting hash as a key for an encryption. And the reason it's bad is not because SHA-256 is insecure or something. It's actually very secure and it's time consuming a little bit, but it's also very fast for a hacker to generate rainbow tables. So what am I talking about? If a hacker steals the password hash and takes it into his home, what he can do is he can grab a word list, maybe of 1,000,000 words, then hash each word into SHA-256 hashes and then compare the resulting hashes with the stolen hashes. If those two hashes match, then the hacker can know what password was actually used to generate the hash. That's why directly using a plain old simple hash function for generating a key for an encryption to work is not very secure. So that's why we use password-based key derivation function to slow down a hacker. Also, PBKDF2 is not susceptible to rainbow table attacks because in PBKDF2, the iterations, as you can see in the last parameter, the iterations that are used can be any. So if the hacker doesn't exactly know how many iterations were used, it is going to be very hard for the hacker to actually generate the hashes from the word list. Alright, so before that, what a rainbow table is, when you are converting each words in your word list, then hashing it to a SHA-256 hash and then comparing the stolen hash with the resulting hash, that is time consuming, right? So what you can do, you can pre-compute all the hashes from your word list and keep it to a separate file. Alright, now what you can do is you can just simply compare all the resulting hashes with the stolen hash, and if any of them had a match, you would just simply know what the password was, because this process is much faster, right? You can just directly download a rainbow table from the internet or create one for yourself, and then the process of brute forcing is much less time consuming and easier. So PBKDF2 saves us from that because it's also time consuming. So now let's get directly to PBKDF2. So you can see something called a PRF here, which is the pseudo-random function. The word, which is the second parameter, is basically the password. Now there is the salt. I'm just going to explain what salt is in a minute. Then there is DK length, which is the derived key length. You can actually set a derived key length. For example, SHA-256 spits out a 32-byte value, right? But with the DK length or the derived key length, if you want a value of 40 bytes, you can do that. So, and lastly, the iterations, which I just told. So what is a salt? So salt is like a randomizer, right? As I have told you in the second video of this tutorial. So what salt does is, for example, the password maybe is QWERTY, and the salt is a randomized value, maybe which represents the word hello. So what it does, in a pre-hashing way, that the salt is appended or prepended to the actual password, making it salt QWERTY or QWERTY salt, and then the whole thing is hashed. Now, if even the hacker has a rainbow table, the hacker does not have the salt already added to the original word lists, and the rainbow table is not a salted rainbow table, because he didn't generate a salted rainbow table, he just generated rainbow tables for regular words. So if he has to do that, he had to append the salt with each of the words in the word list and then again recompute the hashes. That is also time consuming, and you cannot know the salt by default because the salt is also stored in the database, but a lot of hacking methods are needed for you to get all the original hashes, the salts, the IVs. These, all of the things are very much time consuming. So if a hacker doesn't have access to everything of a website, he cannot possibly know everything that is used to compute a hash. So a salt is used that way, but even that way you can pretty much easily recompute a salted version of a rainbow table, right? But again, PBKDF2 saves that from that. How? Because it's used in a slightly different way, and I'm going to say it right now. What PRF is in this case is the actual hashing algorithm that is used, and PRF is not just a simple SHA-256 or a SHA-1 hash, but it's an HMAC version of the hash, and I just told you what HMAC is, right? So in this case, maybe let's say the PRF is SHA-256. Then the password, the salt, the derived key length, maybe it's 256 bits or 32 bytes. Then the iterations. Now, what happens is, if you remember this part, which is going to be the HMAC, again if I say that the message is first appended to the key, then it's hashed, and again the resulting hash is appended to the outer key and then again hashed. This is basically HMAC. So this same process is used in the PRF within the PBKDF2. So what happens is the word or the password is used as the key within the HMAC, and the salt is actually used as the message for the HMAC, because the HMAC has two parts, right? The key and the message. So in PBKDF2, the salt is used in the place of M and the password is used in the place of K. Now these K will be XORed with the inner pad and this K will be XORed with the outer pad, but it's a topic of another day. So anyways, now the iterations is the number of iterations that PBKDF2 will loop. So it is not as easy as the resulting hash from the PRF is again and again and again iterated and hashed, but it's a little bit complex because the hash from the previous loop, for example the first loop, which uses the word as the key and the salt as the message, will generate the hash in the first loop, right? And that hash is not again just simply iterated, but that hash is used as the message for the next consecutive loops. Alright, if I say that again, the resulting hash from the PRF, where the word is used as the key and the salt is used in the message, that resulting hash is not just looped again and again, but that resulting hash is actually used as the message within the HMAC, and this process is looped for the number of provided iterations. That makes PBKDF2 very slow and secure. So that way a hacker needs a huge resources to actually recompute every PBKDF2 hashes for every password in his word list. So now you know what PBKDF2 is. Let's move on to the next tutorial.